Now let's talk about shared memory jobs or OpenMP jobs. Just a reminder, in a shared memory job, you have a single Unix process. So Unix process is the smallest independent unit of computing in Unix. And this process can have multiple threads, and each thread will have access to the same shared memory space, and each thread will run on its own processor. This way you can utilize multi-core parallelism on a single node. OpenMP is one of the ways to do shared memory programming. It's not the only one, but OpenMP is really easy to use. So essentially you enclose your parallel blocks or parallel loops into special OpenMP statements. And this way you almost automatically parallelize your code. The downside of OpenMP is that you can only use processes on the same node. You cannot scale beyond a single node. So let me show how you can submit an OpenMP job on the cluster. Here I'm back to the training cluster, and the code we're going to run is called sharedpi.c. And here's the entire code. So it's very similar to the original code pi.c, except that now here we have the loop that is enclosed into this pragma statement that parallelizes this loop. So we have 10 billion elements. And let's say if we run this on 10 processes on the same node, then 10 billion elements will be broken into 10 groups. Each thread will process its own group of billion elements. And then each thread will run on its own processor. This way you can actually speed up calculations roughly by a factor of 10. Of course, on the training cluster, we don't have nodes with 10 processes. Our nodes on KCP have only 2 processes, and so that means that you can only use 2 threads at most with OpenMP jobs. So let me compile this code. Because I already have the make file, I'm going to say make OpenMP, and that will run the following command, and -f OpenMP is the flag to produce a shared memory code. So the executable is called OpenMP now. And then let's open the job submission script. So it's called job_openmp.sh. And here, what we want to modify is, well, first of all, you want to set, oops, let me erase this. You want to set the higher memory limit, and this is for the entire job. So I set it to 1000 megabytes, and then we're asking for 2 CPUs per task. So once again, this is really important. We're submitting a job that will launch a single Unix process, a single task, but this task will use 2 cores. So there are 2 CPUs per task. And then this is the runtime in a slightly different format. So we're saying 0 days, 0 hours, and 5 minutes. Okay, so 5 minutes, 1000 megabytes in total. And then inside this job, once it starts running, we'll have access to a number of Slurm variables. One of them is Slurm CPUs per task, which will store the number of CPUs that are part of our job. So this variable is going to be equal to 2 inside the running job. And then the value of this variable is passed to this variable, OpenMP number of threads. So it's also set to 2. And this variable, OpenMP number of threads, will be passed to the running code OpenMP. So that's how the code at runtime knows how many processes it has access to. So because this variable is equal to 2, the code at runtime will know that it needs to launch 2 threads, and each thread will run on its own processor. And before the executable code, we have echo running on 2 cores, or how many cores we have in our shared memory job. So let's submit this script. I'm going to save it. So let me cut it to make sure I have everything correctly. So yes, 2 cores, 5 minutes, and 1000 megabytes. And then we already compiled the code. We have OpenMP right here. And then I'm going to say as batch, followed by the script name, job openmp.sh. And we submitted batch job 6. So let me type SQ. So here's my job is running. And you see it's 3 seconds into the run. And it's using 2 cores on a single node. So this is indeed a shared memory job. We're using 2 cores on a single node. Total amount of memory is 1000 megabytes. And let's just wait for it to finish. Here it just finished. The output should go into the file slom-job-id, so it's 6.out. And here's the output of the code. Running on 2 cores. This line echo running on so many cores. And then we have the output of our shared memory code. One thing I have not mentioned so far is that you can actually pass different flags to the sq command. So you can say sq -u, your username, and that will list all current jobs, whether they are currently scheduled to run, they're still waiting in the queue, or they're running. If you want to show only running jobs, you can say sq -u, your username, -t running, or you can say -t pending, or both if you want to do it that way. For a job that has finished, you can also print out its various parameters. One command would be saccount as acct -j followed by a job ID. And then optionally, you can specify various flags. For example, you want to print only the job ID, the maximum resident set size, so the amount of memory this job used, and the elapsed time. Let's just do this for our shared memory job. So I'm going to say sacct -j job ID, and then -- equal to job ID, maximum resident set size, and elapse. Job ID, maximum resident set size, so memory, and then elapsed. That will show that the job used roughly 450 kilobytes of memory, so that's actually a tiny amount, and then it ran for 44 wall clock time seconds. And the job ID was job number 6. Another command that is useful is sf, as efficiency, slom efficiency, followed by the job ID. And this job will show you the efficiency of your code, along with various parameters of your job. So for example, memory utilized, the same amount as you saw before, 452 kilobytes. Memory efficiency means that we used very little memory out of the 1000 megabytes that we asked. And then wall clock time, 44 seconds. We were running on 2 cores, 1 node. And this is the CPU time. We used 1 minute and 24 seconds of CPU time in 44 wall clock seconds. And that translates into this 95% efficiency for CPU usage.